This is the western section of the circle. We can see this is trilithon 4. We're looking here at pillar 21. This is the T4 line. We can see the T4 line is currently in this gap area preceding pillar 21. If we just look further along, this large gap area here is where we've had the missing pillar. There was a pillar here at some point, but it has since been removed. This is pillar 19, which was the west position, facing opposite, obviously facing due east, and this is the point where on the equinox the sun will be rising directly opposite this point. So this is 7.5 in our 30-hour time system. So this pillar overall represents the 7th hour. This here is a lintel. It would have been raised up in the air when the pillars were here, and this would have been a gap, and this would have represented the 8th hour when the beam of light passed off this pillar onto this gap. It would have been considered as moving from the 7th hour to the 8th hour. Obviously, where we have our missing pillar, this would be in the 9th hour, and so our beam of light, our T4 line, is on the 10th position in the 10th hour. And considering the pillar would have ended somewhere around here, we can think, or we can see, the line is roughly halfway along that position. Now, I'll just move this along a little bit, but we can see we've got roughly 9:22. This is August the 25th, so this is in British summertime, so we have to convert this back to GMT, Greenwich Mean Time, which gives us 8:22 in the morning. Now, we need to convert that time into 30-hour time, so we divide the number of minutes with 22 by the 60 minutes of the 60-minute hour, and this gives us the percentage of the hour those minutes represent. You have to use the quotient between the degrees per hour rate of the time system. So in the 24-hour time system, the sun moves 15 degrees per hour. In the 30-hour time system, it moves 12 degrees per hour. And if we divide 15 by 12, we arrive at 1.25, so that's our quotient. So it's 8:22 in the morning, and this figure represents 22 minutes as a percentage of the hour. We times this by the quotient, and we arrive at, obviously, the 10. This gives us the hour, 10th hour, which is our 10th position, and we have to figure this out in terms of minutes. This is the percentage of the hour. So of course, if there are 48 minutes in a 30-hour hour, that's because 1,440 the total minutes in a day divided by the 30 hours of the day gives us 48 minutes per hour. So the amount of seconds in the minute has to be a base 10 fraction of how many minutes there are in the hour. So we've got 48 seconds in a Stonehenge minute times 45.83 recurring. This poetic license, because we're using recurring numbers, this is basically 22 minutes past. So this is telling us that 22 minutes past 8, 24-hour time is 22 minutes past 10, 30-hour time. So of course, with this position here being position 10, we'd expect this line to be roughly halfway along this position. Obviously, if there's 48 minutes in a Stonehenge hour, there are 24 minutes in the half hour. So 22 minutes past, we'd expect it to be practically halfway along this line. It's exactly where we find it. This is the T4 line striking our first on the hour position. This is pillar 21, gone from 10 to 11, the 11th hour. This is happening when the sun's at 115 degrees azimuth. On May the 5th, this would be happening at 8:48 local mean time, 24-hour time, which is on to the 11th hour, Stonehenge time. So I just want to show you the watch in this clip. Sorry, it pans across a bit. We do get a clear shot of the watch. So this is 8:44 GMT. This is reading in BST. So it'll be 8:44 on August the 25th. Obviously, we're not on our calibration date. At this point the monument's actually reading early by 4 minutes. The line is really quite faint. You can just make out the T4 line shining down here. This is pillar 21, and we can see it moving off the pillar onto this gap here. The sun is at 128 degrees azimuth at this point. On May the 5th, this will be happening at 9:36 local mean time. In terms of 24-hour time, that's 9:36. 30-hour time, 9:36, equates to 12. This was position 11, so this is position 12. I'll just show you the watch. So we can see it's 9:35 GMT. So at this point the monument's reading 1 minute early in terms of GMT. 6 minutes later, as we can see here. And the reason we're seeing this is because the sun had come out at this point. The T4 line can be seen a lot clearer. In 6 minutes it's obviously moved a certain amount, but we can clearly see that it's on the 12th position here. The time here is 10:24 GMT. This footage was actually captured a few minutes early. The intended time really was 10:26 on August 25th. At this time the sun was hitting 143 degrees azimuth, so that was really the intended time. We've got it here a few minutes early, meaning that the line is just under a degree short of its actual target. Nonetheless, you can see that it is moving on to 143 degrees azimuth, and it's moving on to the next hour target, pillar 22. On May the 5th, it would have been hitting 143 degrees azimuth at 10:24 local mean time, equating to 13 AM Stonehenge time, marking position 13 or the 13th hour. So we've gone from 10:30, 11, 12, 13. Halfway along this pillar, this line will get so thin that we'll just have a block of shadow here, and this line will no longer be there. An aspect that I haven't discussed so far, obviously the builders of Stonehenge would have had no concept of GMT, Greenwich Mean Time. The times you've been seeing on the watch were in British summertime. I've been converting them into Greenwich Mean Time. The Stonehenge architects would have worked in local mean time, and there's actually a 7-minute difference between Greenwich Mean Time and local mean time for the location of Stonehenge, because it's 1.8 degrees from Greenwich. That's a 7-minute difference. So this actually means that we should be deducting 7 minutes from all of our GMT times. You'll have noticed that the times relating to the hours earlier on were early by a couple of minutes in most cases. When by the time we got to this clip, the sun is hitting azimuth 143 degrees at 10:26 GMT, so it's actually now 2 minutes late. So obviously, taking into account the difference between Greenwich Mean Time and local mean time, it's still running 5 minutes early. Just the kind of illusion of it becoming late at this point in the morning is caused by the difference in local mean time and Greenwich Mean Time, that 7-minute difference. Of course, as it carried on towards midday, the true sun does actually catch up with mean time. For midday and solar noon only ever occur a maximum of 15 minutes apart. So basically the process flips, and for the afternoon, where for most of the morning the monument was reading early, for most of the afternoon on the August the 25th it will then read late. To really understand more about why this happens, to understand more about the monument, about its calibration, you need to go to cypherworks.wordpress.com. You can also feel free to send an email provided here, and please spread the word about this. This is a new theory. It does require a wider attention to it. So if you're interested in this, if you think you know anyone that will be interested in this, please share it, tell people about it, refer people to this video and to the WordPress blog site. There is a download on there to a paper that I have written exploring earth clock theory, and the paper's called Stonehenge, a proto-sundial with bias towards summer.